I'm Brendan McMahon, a research scientist at Google, based out of the Seattle office. And I work on a team that's developing technologies for federated learning, doing the fundamental research to increase the set of machine learning models we can train in this way, and also developing practical systems. So I work broadly on topics of machine learning and privacy, and it's worth pointing out that privacy is a very broad area. I don't think there's a consensus about what exactly privacy means. It's very context specific and application specific. So I really think of my work as building technologies that enable privacy in a lot of different contexts, but the specific decisions about how to use those technologies will vary by application. So it's really a distinction between kind of privacy policy. So if you have a particular product you're building, what's the right way to respect the user with that product, with that use of data? And my goal is to develop technologies that expand the set of products we can build, expand the set of machine learning models we can train, while also respecting the user. I think that's kind of a good general. Privacy is one of many kind of terms that falls under that general banner that we really believe in at Google, which is always respecting the user. So this also touches and often intersects with things like ML fairness and those kind of issues. But privacy itself is very broad. I've been reading this book by Ari Waldman called Privacy as Trust, which takes the kind of more of a legal perspective, which is quite outside of my wheelhouse, but is very interesting. So I think it's important that those kind of dialogues happening elsewhere in society inform the technologies we're building. But at the end of the day, I'm trying to build enabling technologies that can be applied differently in different contexts to provide more private and more respectful solutions to users. Privacy-preserving machine learning is actually a little bit easier to talk about than privacy in general, because in many cases, especially when you are training kind of a single global predictive model, that goal is very well aligned with privacy, and in a sense that you can actually make quite technical and precise. There's been a very interesting line of work exploring this, not by my group, but more broadly in the ML theory community. But the basic idea is with machine learning, what we're trying to do is come up with a general predictive model that will predict well on new data. So that means that if you're in some sense violating privacy, if you're memorizing the training data, that's going against the goals of machine learning as well as the goals of privacy. Or putting it another way, if your machine learning model is too sensitive to any one training example or any one user's data, you're going to run into problems on the machine learning front as well. So in general, machine learning and privacy fit together nicely, and so a lot of the work there, especially around, say, differential privacy, is about taking some of that existing ideas around overfitting and then kind of formalizing and making sure we can kind of prove that we're not overfitting to any one example in the data set. One good summary, I guess, to think about privacy and machine learning, there's other goals there, but a big one is to prevent your model from memorizing specific training examples in a way that somebody who has access to the model could later reconstruct those. Privacy can mean a lot of different things in a lot of different contexts. So I don't think, well, we have very useful technical definitions of privacy, and I think if you can achieve those, often that might be a pretty broadly accepted notion of privacy. There's a lot of nuance. You have to take into account the expectations of the people involved, the potential power imbalances there, trust. There's a lot of different dynamics, and I think that's why decisions around privacy need to be very carefully considered and made by people with a broad range of backgrounds. Federated learning is not really a specific algorithm for machine learning. It's really a setting for machine learning, or a general approach to machine learning. The rough idea is that in kind of traditional machine learning, maybe that's the place to start, you assume you have all of the data there on your computer or in a data center, you run an iterative training process on it, and you come up with a global model. Federated learning kind of asks the question, what if we want to train that same model, but we don't want to have direct access to the training data. We're going to leave the training data distributed and decentralized on, say, a fleet of mobile devices. So the data stays scattered across millions of mobile devices. Can we develop algorithms that let us still train that same global model that we want, that same predictive model, without direct access to the data? I wouldn't say that federated learning necessarily protects privacy. I think the relationship there is a little bit more subtle. Federated learning is kind of a tool you can have in your toolbox that, when applied carefully and with the appropriate considerations, can provide enhanced privacy. But there's a lot of other tools that you can use to do this. I mean, Google has a large number of teams and puts a huge amount of effort into developing different privacy technologies that are applicable in different circumstances. So federated learning is increasingly becoming an important one of those tools, but it's one of many. And the flip side is also kind of true, that just because you're doing federated learning doesn't mean you're really respecting the user. You have to be careful about how you configure it. The specific parameters matter, and of course the goal of what you're trying to learn matters as well. So when you take all of those things into account, though, federated learning can be a very powerful tool, and it has a couple of clear advantages when it's applicable. The main one is that the raw training data, the user data, often it's user-generated data or privacy-sensitive data that we want to train on when we're doing federated learning, we can leave that on the user's device, so they kind of stay in complete control of that data. There's other ways to give users control of their data as well, but that's a very tangible one. So the data stays decentralized. What's communicated then back to the server isn't the raw data, but it's a focused update. And I think this is a general principle in privacy technology. You only want to kind of give access to the data for a specific purpose. And that's kind of true to a very large extent with federated learning. What we're sending to the server is an update that's really only designed and is carefully constructed to be the minimal thing that will improve this global predictive model that we're trying to train. So there's the focused nature of the updates. The other thing that's nice and follows closely from the fact that those updates are so focused is that we can treat them as totally ephemeral. They're never written to disk or serialized. We immediately aggregate them with the updates from hundreds of other users and then apply that average update to the model. So there's no persistent data storage that's needed. The only thing that's persisted is the shared global model that eventually then gets sent back to users to make their devices better. Our focus has been on using federated learning on mobile devices. There's a bunch of reasons for that. Mobile devices have access to really rich data, both via sensors, things like GPS, microphone, camera, and so on, to understand the real world. And then our phones also increasingly mediate a huge amount of our digital interaction, communication, content consumption, and so on. So there's extremely rich but also extremely privacy-sensitive data on mobile phones. If that data is used carefully with machine learning, it can power really amazing experiences for users. It can make your phone do things that were just unimaginable even a few years ago. But it's necessary to do that, obviously given the nature of the data, in a very privacy-sensitive way. So federated learning is a tool to kind of break what sometimes comes up as a false dichotomy, that if you want to have really sophisticated machine learning, you have to give up privacy. And we're trying to kind of expand the set of problems and machine learning tasks where we can really decouple those things. We can provide those amazing experiences without needing access to raw data. So that has led to a lot of the applications on Android phones that Google has done so far. But we're seeing a lot of broader interest. Federated learning has a few kind of defining characteristics when we were first kind of coming up with a term and really realizing that we needed a different term. This isn't the same thing as just standard distributed optimization. One of the big differences is how broadly the data is distributed. So we're looking at a data set that's not spread over 10 or 100 nodes in a data center. We're talking about data that's distributed over millions of devices or even more. So it's massively distributed. The way the data is distributed is also quite different. If you have the data in the data center, you can shuffle the data, and so it all is kind of, each node has the same amount of data, it's all drawn IID. That makes things much easier from a learning and optimization perspective. In the federated setting, the data on each device could be quite different in character. No one user's data is really going to be reflective of the overall population trends. So that means it's really necessary to average and to take into account those differences coming from this very diverse set of users in order to train a good shared model. Another defining characteristic really is the unreliability and limited availability of those devices. We're very careful to only train on devices in a way that won't impact the user experience at all. So we don't want to drain the battery, we only train when the phone is plugged in and mostly charged. We only want to do network communication to say download a model or send a model update when the phone is on an unmetered Wi-Fi network. And since the training can be a somewhat heavyweight processing, we only want to do that when the phone is idle. That means we're typically doing federated learning at night local time. Think, your phone is plugged in and charging on your home Wi-Fi. That's very good for the user. It means that federated learning shouldn't negatively impact you in any way. On the other hand, it presents some really interesting challenges from a machine learning perspective, because we can't access any data we want at any time. We need to wait for the phone to connect to us and say, hey, I'm available to do some training now. And so that produces these very distinct diurnal patterns in which phones are available for training when, because of that day-night cycle. So that's an issue that just doesn't come up in the data center, but is important in federated learning. So that's kind of the set of challenges that we saw as being specific to federated learning, and they're very important to these. They all come up in these applications on mobile devices. But as we've been talking about this more, we're seeing a lot of interest in other domains as well, which might not fit all of those characteristics, but still have some of them, right? You still have some of the same privacy concerns, but maybe things aren't as massively distributed, right? So there's various scenarios where you might want to do federated learning across organizations. So then you might not have millions of organizations, maybe you only have tens of organizations. It's not as massively distributed, but similar techniques can still be useful. So I think one of the things that's really exciting about this area is the breadth of use cases that people are now considering applying federated learning techniques to. So federated learning is great for a wide range of problems, but it's not always the best technique or always even applicable. And I think that's really important to point out. A canonical example of a really good fit for machine learning would be a problem where the training data is obviously very privacy sensitive. It's important to train on training data from the right distribution. So you want to train on the actual private data from real users' interactions with their phones. And you also have to have a machine learning problem, at least right now, where the labels, if you're doing a supervised learning problem, are naturally generated on device. So a really good example of this, and one of the main collaborations we've had, is for next word prediction in a mobile keyboard, right? So it's very important to train on data from the right distribution. If you train a language model for your mobile keyboard on Wikipedia data, it's not going to be a very good language model because people don't write Wikipedia articles the same way they write text messages. The use of language is very different. So it's important to train on the real data, but the real data is also very privacy sensitive. So that makes it a good fit for federated learning. The other thing that makes that a really good fit for federated learning, if we incorrectly suggest the next word you are going to type, usually the person will just type that word out. So we know what we should have predicted afterwards. So that naturally generated user feedback signal is really important. There's a lot of really important machine learning problems that don't necessarily meet those criteria. If you already have a perfectly good training data set for the problem you want to solve in the data center, it's probably going to be a lot easier just to train on that data. You probably don't need federated learning. Maybe you can train on purely public data. There's probably some language tasks, for example, where training on Wikipedia data works just fine, and that's going to be much easier. Another example of a class of problems where with more research, maybe we can extend federated learning in this way. But right now, it's less obvious how you would do something like train an image recognition model. Say you want to train a model to recognize different dog breeds. For that kind of a model, you really need carefully labeled data that identifies what breed of dog is in what picture. And typically, when people are using their mobile phones, they're not providing that kind of a feedback signal. And so it's going to be hard to train that type of a model with federated learning. Now, there's some semi-supervised or unsupervised techniques that maybe you could do, but that's more of an open research question right now. Another example of a problem that's right now not a great fit for federated learning, though I think some components in federated learning will eventually be able to help things there, are problems where you're ranking a really large inventory of results for the user. So think about things like suggesting a YouTube video for you to watch. The problem is it's just not practical to keep a full index of all of the YouTube videos on your phone. So a server has to be in the loop there, both at training time and at prediction time. You can also think about web search is in the same category. There's a set of problems where federated learning is applicable, and then we're interested kind of to continue pushing the research out to make that set as big as possible, but it's certainly not a solution for every machine learning problem. We've been talking about federated learning publicly for a couple of years now, initially with some research papers, and we had a blog post on the Google Research blog that actually inspired quite a bit of interest. We really think that being very transparent in what we're doing with federated learning is really important. I mean, this is new technology. Some of the nuances, especially when you combine it with things like differential privacy, are quite complicated. So we want to be kind of explaining this technology to as many people as are interested, and also getting feedback from the research community and the broader community of users about the technology, so we develop things in the best way possible. One of the really interesting, I think, side effects of that external communication we've done, though, is that this has inspired a lot of interest, entrepreneurial interest, and in different areas. I won't name any names, but a quick Google search will reveal a lot of different companies that are interested in federated learning technologies, and they're seeing applications in areas that we hadn't even really considered yet. So that's very exciting. It was to the point that Google Ventures actually reached out to my team to learn more about the technology, because they were hearing this term coming up in conversations with multiple startups. So it's an idea that I think is grown far beyond kind of the initial use cases in Android we were targeting or have targeted so far. The genesis of the kind of the idea of federated learning really goes back to a team that Blaise Aguirre-Arquis has been building in Seattle for a while. And I think he deserves a lot of credit for kind of pointing out the trends that, once you appreciated them, made the need for federated learning pretty clear. One of those trends was just looking at the increasing scope of data that mobile devices have access to. I mean, it's really unprecedented. And when you combine that with the fact that people almost always have their mobile devices with them, that's an incredibly rich source of data. Again, thinking not only about digital interactions, communication, content consumption, but also really the device has incredible access to the real world as well via accelerometers, cameras, microphones, GPS, and so on. So one of the trends was this increasing amount of data and richness of sensors on mobile devices. Coupled to that is the increasing computational capabilities of mobile devices. And then at the same time, we've had this kind of resurgence of deep learning. The set of applications where machine learning can really provide state-of-the-art results has been growing very dramatically over the past few years. And one of the main things that's driven the success of modern deep learning approaches is the availability of very large, rich data sets. So when you put those two trends together, or three trends together, it becomes fairly clear that there's going to be increasing machine learning happening on data from mobile devices. And that very much leaves open the question, what shape is that machine learning going to take? The default, I think, in the industry is, well, you log that data to the data center, and then you run your machine learning algorithms locally there. And as you start talking about these really sensitive privacy sources of private data, that just doesn't really make sense anymore. You either have to log data that you probably shouldn't be logging just to do machine learning, or you just don't create those products or those amazing experiences. So we started thinking about this problem, and it wasn't really clear it was possible, but the idea of training these machine learning models in a way that lets you leave the data at its kind of source of origin, taking advantage of the increasing computational capabilities of these edge devices, particularly mobile phones, was a clear challenge. So once we had that, we kind of started a research program, first trying out kind of smaller models, working up to full deep networks, showing in simulation that it was actually possible to train models in this way. And the project has just kind of grown from there. One of the really exciting things we've seen is taking this idea of federated learning, from what really was a research project and something that we weren't even sure was possible, and seeing it make its way into real Google products that are improving user experiences for really large numbers of people. One of the big collaborations we've had is with the Gboard mobile keyboard team. Mobile keyboards aren't something you think about a lot, but they're involved in a huge amount of mobile phone use, and I think they're still, everybody would agree, not nearly as good as they could be. So there's clear space there for machine learning models and federated learning to really improve user experiences. So we've launched a couple of models with them. One is for next word prediction. So predicting the next word you type based on what you've typed so far. This is a great application of federated learning because it lets us adapt to the constantly changing usage of language in the real world. Another application there is the Google Keyboard can suggest related Google queries that you might want to do. Sometimes that feature is useful, but sometimes it isn't. So by using federated learning on the feedback signal of whether or not users are deciding to run those Google queries, we can really improve triggering for that feature so that we only show those queries when they're really useful to users. Another application we've talked about is in settings search. So I think on Android phones, there's probably over 1,000 different setting and configuration options. So by looking at which of those setting options people go to and when they're searching for different things or when their phone is in different state, we can provide a pretty good prediction of which setting is actually relevant to you right now. And that's improved the user experience of that feature quite a bit. So those are some of the things we've talked about now, and I should point out that the Gboard team actually has published a couple of papers talking about both of the use cases I mentioned, and so that's a great source to find out more about how this technology is actually being used in practice at Google. The applications to Gboard, next word prediction, settings search, those were some of the first applications we picked because they really are a good fit. They're kind of canonical examples of good federated learning problems where the technology has a lot to offer. Using mobile keyboards, it's really important to train on data from the right distribution. The data is very privacy sensitive, and users give us great feedback by what they continue to type on what the label should be, so that we can develop a set of on-device training data that's just right for improving that model. So in some sense, you could say that we picked these because they were low-hanging fruit. They were just very natural fits for the types of federated learning, the types of problems federated learning is good to solve. But I think another reason is just that the Gboard team was a really good partner. They were excited about this technology and willing to try out something new. So they get a lot of credit for actually making this happen in production. A common question we get from teams at Google that are considering using federated learning is, how does federated learning impact model quality? And the answer there has a couple of different dimensions. One is on just the axis of training speed. Because phone network connections are many orders of magnitude slower than what we have in the data center, there's an inherent bottleneck there in training that even with the sophisticated algorithms we've developed, mean that federated learning is probably going to take longer in terms of wall clock time to train a comparable model in the data center. But that would be under the assumption that you have the same data in the data center and on the mobile devices you're using federated learning on. When that's the case, for example, when we've done these kind of experiments using simulation on public data sets, we can usually get to the same level of accuracy for the final model with federated learning. It just takes a little longer. But that's really kind of only half the story. And I think when teams really get excited about federated learning is when they start thinking about not just the accuracy they could get from the data that they currently have, which is often proxy data, not as good a fit for the problem as they would like. Once you're using on-device data, it becomes quite possible to train on more data or to have more representative data or even to add features that you wouldn't have access to. For example, if you're training a language model on Wikipedia data, the model has no idea who you're chatting with. Say you're actually writing a text message, that model doesn't know anything about what app you're using or who you're chatting with. Whereas if you're actually using the actual on-device usage data, you can add context features that potentially make the model much, much more accurate than training on the more limited proxy data you would have in a data center. So the answer there, I think, is often once you spend a little time on it, federated learning can surpass what you were doing before. Something that comes up with federated learning is that you are shipping the model to a bunch of devices in order to train it there. And there are some models where, for IP reasons or otherwise, you might want to protect the architecture of the model, and that's a challenging problem. I think there are some techniques from the encryption, homomorphic encryption side of things. Also, there's some things you may be able to do with trusted hardware, secure enclaves, but that's a hard problem that we're still thinking about. Right now, though, I think the benefits of federated learning mean that, at least internally, that hasn't been a particularly big concern. One of the main reasons for that is that this issue really isn't unique to federated learning. Most of the models we want to train for federated learning are already models that are running on device to make predictions. There's a bunch of advantages you get for running the models on device for predictions, so that the app or the experience works when you're offline. You don't have to use Wi-Fi, latency can be much lower, and so on. So for models where you're already using the model on device, then training them with federated learning doesn't really add any additional concerns about protecting the model itself. Another concern that another privacy-related concern that comes up in machine learning, both federated machine learning and data center-based machine learning, is the question of whether the model can memorize any specific training examples. So this isn't unique to federated learning, but it's certainly a concern there, since federated learning is often used on user data that's quite privacy sensitive. A good example of this is in language modeling. We want a good next word prediction model for the Google keyboard, but if it correctly completes the sentence, Brendan McMahon's credit card number is such and such, clearly we would have a big problem from a privacy perspective. The good news is that there's an established set of mathematical techniques and a formal definition of privacy, differential privacy, that directly addresses this question. Informally, differential privacy just says we want to learn something in aggregate without learning too much in a mathematically bounded way about any one user's data. So we've collaborated with a number of other researchers at Google to develop techniques for training large-scale real-world deep networks with differential privacy. And this is differential privacy in the trusted aggregator or central sense. So the concern here really is making sure that that final model that you're, say, going to put on devices to make predictions doesn't memorize user data. This is still a pretty hard thing to do. I would say that this technology is in its early stages, maybe even more so than federated learning. So it can't be applied to all models, and applying it is quite tricky. But it's certainly the gold standard of solving this kind of memorization problem, or proving that kind of memorization can't happen. So we did some work that extended these ideas to federated learning. And it's actually very nice. There's a nice synergy here. One thing is that the more times you kind of access private data, the more cost in privacy there is in the differential privacy sense. For federated learning, we'd already developed techniques that minimize the amount of communication needed, which corresponds to accesses of data in order to train models. So those techniques we developed to make federated learning possible and more efficient also are really beneficial from a privacy perspective. The other thing that is a nice synergy between federated learning and differential privacy is federated learning kind of naturally accesses all of one user's data at one time. And this proves to be really useful when you want to add differential privacy as a layer on top of that, because you need to bound the contribution of any one user's data and make sure that it doesn't have too much influence on the model. So the fact that one user's data isn't kind of scattered through the data set, but is concentrated, and we compute a single update to the model based on a user's data, means that we can bound the contribution of that data much more easily. So we have one research paper out on this technique, and I think it's a very promising area. The other side of it, though, is that in many cases, differential privacy is a much stronger guarantee than you really need to prevent these kinds of memorization attacks. There's a parameter that says how differentially private something is, and even large values of that parameter can still be sufficient to prevent model memorization. So another really interesting line of work at Google is developing techniques to measure the amount a model is memorizing, so that you can have an empirical test that says, at least according to our measurement technique, this model isn't memorizing any one user's data. Secure aggregation is another technique we use to provide stronger guarantees on top of kind of a standard federated learning implementation. The goal there is to limit even further the amount that the server that's coordinating the federated learning can kind of learn about updates. One of the nice properties, and this is not by coincidence, of the algorithms we've developed for federated learning is that they don't kind of need individual user updates. The algorithms we use really only want a simple average of the updates from a large number of users. So secure aggregation provides us a way to basically cryptographically guarantee that the server running the federated learning algorithm or coordinating the federated learning algorithm can't learn any one user's update. Instead, each user sends kind of an encrypted update that includes a noise mask, so that by itself each of those updates is gibberish. But if enough users contribute updates, and that's a parameter that we can configure based on privacy and other considerations, then we can decrypt not an individual update, but the sum or average of all of those updates. So this is taking that principle, I would say, of kind of focus collection even farther. All we really need access to is the average update. So let's try to use cryptography so that's really exactly all that we get. We've seen a lot of interest expressed about federated learning from a bunch of different companies and open source projects. But right now, as far as I know, and I haven't checked carefully recently, I don't think anybody else has kind of deployed federated learning for practical applications at the scale Google has. But I expect that to change relatively quickly. Yeah, my phone does run federated learning for the use cases that we've deployed so far. So I use the Gboard keyboard and use setting search, and it's pretty cool to know that that's running on my phone. Though because of all of the links we go to make sure that training doesn't impact the user experiences, it's not something that I notice on a day-to-day basis or at all.